Okay, so consider the problem of computing the area under the curve of a function. Right, so our example here is that of y equals 6 plus x minus x squared in between 0 and 3. And so this is the area we're considering here. Right, and we want to eventually get at the value for the area, which is exact. But for now, let's think about ways in which we can approximate this area. I mean, one way would be, well, maybe we can say this looks like a triangular shape. So this area is an approximation of the area we're considering. And this area is 6 times 3 divided by 2, which is 9. I mean, it's not a very good approximation, but it is an approximation nonetheless. Right? And maybe there's another way for you to approximate this area, maybe with a rectangle, but then you'd have to know what the sides are to compute that area. So this isn't really a nice approximation, so I'm going to erase this. Well, what if instead we cut the area off like this, observing that the area on the left can be approximated by a rectangle and the area on the right by a triangle. Right, so this seems a bit better. Right, this rectangle has area 6, while this triangle has area, well, that's 6 times 2 divided by 2, which is also 6. So now we can say the area is approximately 12. And now this seems a bit better, right? Clearly it's still an underestimate. We're missing this part here under the curve, and we're missing this part. But it seems close. Of course, this technique that we just did here is not really generalizable to every type of curve. Right? There may be some curves where you don't know what the shape looks like, whether you'll be able to use triangles or rectangles to approximate these areas. And so what we really like is a systematic way to do this kind of approximation, right? Using rectangles, which is the easiest to compute. It's just length times width, or height times width. And so what if we were just to use rectangles? Okay. So let's see what happens when we divide. It's not. Okay, that's better. Okay, so let's divide this interval from 0 to 3 into 3 parts. Right? One from 0 to 1, one part from 1 to 2, one part from 2 to 3. And for each part, take a rectangle that approximates the area of the curve, or the area under the curve in that region. So for 0 to 1, maybe we can take this rectangle, taking the height of the rectangle to be this right end point of the interval at 1. From 1 to 2, let's just follow the same train of thought here. Let's pick the right end point of the interval from 1 to 2 and set that as the height of our rectangle. And let's do the same thing for the last interval, which is now 3. X equals 3 is the right endpoint. Oh, but wait, 3, when you plug it into your function here, actually it just gives you exactly 0. So this is a rectangle of 0 height here at the end. So using this as an approximation to the area, Well, now we have 3 rectangles. One with, well, area 6. The width of each one is just 1, right? So it's just 6 times 1 plus 4 times 1 plus 0 times 1, and that's 10. Right? And that's another way we can approximate the area under the curve here. Note that it is a worse approximation than if we had used a triangle instead for the second and third interval. However, what's nice about this technique is that we can extend it to any kind of function and even increase the number n. Right, so in this case, we're dividing the interval from 0 to 3 into 3 slices. What do you think will happen if we increase it further? Well, here are some illustrations. Using the same rule of picking the right endpoint for each interval to tell you what the height is of that rectangle, these are the approximations for n equals 6, 12, and 24. It's 11.875, then 12.719, and 13.117. And note here that for n equals 24, now we're getting to the point where it actually looks really, really close to what the true value is. Right? You're really only missing out on these little spaces here. Right? That you're underestimating the actual area by in this part. And here you're overestimating the area on the left by that small amount. Right? But it does look really nice. It looks really close here. And so, using this idea of, well, when we increase the number of intervals, we get thinner and thinner rectangles. This also means we're getting better and better approximations to the area. Right? So why not just take n to be a very, very large number? N equals 1,000, n equals 2,000. Why not take n and take the limit to infinity? Well, so let's try to find here a general formula for an area approximation for this region that depends on n, right? Where we don't set n to be a number. Right? So that's what we're doing here. We'll find a general formula for our area approximation using n rectangles. And let's just assume we're also sticking with the same method of picking the right, well, not the right technique, but the right endpoint for each interval for the height of our rectangle. So what is it that we have been doing? Well, remember the first step is breaking it up into slices and so on. So let me draw this separately here. If you have an interval from 0 to 3, and you know you'd like n rectangles or n slices of this interval that are equally spaced, that means that each rectangle is going to have a width of, well, the width of the whole interval is 3, and you're dividing it into n equals parts. So the width of each rectangle is 3 over n. Right? They're all equally sized. Well, what's next? After we break it up into all these smaller intervals, well, now for each interval, we need to take the right endpoint and make that the height of your rectangle. Okay. So that's not immediately clear to us what that looks like. And really it's this question of, can we find a general expression for the right endpoint of the ith subinterval, where I ranges from 1 to n, right? So we have n of them, and now we want a general expression for the ith right endpoint. But if you look at what each endpoint is, remember each interval here has length 3 over n, or has width 3 over n. So the first endpoint is going to be exactly 3 over n. Right? It's just 0 is a starting point, and then you're adding the width of one subinterval. The second subinterval is going to be 3 over n plus another 3 over n, right? Or 3 over n times 2. The third right endpoint is going to be 3 over n times 3. And you kind of see a pattern here, right? In general, if you look at the ith subinterval, its left endpoint is going to be 3 over n times I minus 1, right? Because there have been I minus 1 subintervals before that. And the right endpoint is 3 over n times I. Yeah, so that wasn't that hard. Now we have a general expression for the ith right endpoint. So now we can say the ith rectangle, right? Because all of them have different heights. Well, now it has height 3 over n times I. But not just that, right? You're plugging that into the function. Right? So if that's 3 over n, then the height here is the function value of 3 over n, right? It's the y coordinate of this point on top. So it has height f of 3 over n times I. Therefore, the area approximation we have using n subintervals, well, now we can use our sigma notation because we're adding up the areas of all these rectangles together from I equals 1 to n, where in each rectangle you're just multiplying the height, which is 3 over n times I, by the width, which is 3 over n. And this is our general formula for the area approximation using n rectangles and the right endpoint. This is what is called a Riemann sum. Okay? And, well, you might say that still doesn't give us the exact area. Well, remember, I said, now we can actually take the limit. And, well, how would you do that? First, you'd have to plug 3 over n times I into the actual function. And that's 6 plus 3i over n minus 9i squared over n squared multiplied by 3 over n. And using our properties of sigma notation, we can now write this as 18 over n summation of just 1 plus 9 over n squared summation of I minus 27 over n cubed summation of I squared. And I'm not going to complete this calculation, but I encourage you to try it yourself. Take the limit of this expression as n goes to infinity to get the exact value. You should get 13.5 as the answer there. And, well, in general, what this looks like is we can do this for any curve, really. That's nice. By simply doing that same division into subintervals and picking rectangle heights for each subinterval. So instead of 0 and 3, if you have a and b, well, the steps are really the same. First, you take b minus a divided by n, so b minus a is the length of the whole interval, and you divide by n to get the width of each one. Then for each subinterval, follow some rule that tells you what the height is. So we've been using the rule that says take the right endpoint. There are others, right? So you can say xi star is just in general what that point you're taking is from each one. So the height is f at xi star. The approximation is just the sum of all the areas. That's where the sigma notation comes in. And you take the limit as n goes to infinity. Imagine each rectangle being very thin, becoming infinitely thin, right? And so you have the exact area here. And finally, let me just talk about what some other rules are for picking your xi star points here. So the right endpoint, you pick the right one. You can also pick the left endpoint, right? In which case your xi star is going to be a plus I minus 1 delta x, right? Whereas for right endpoints, it was xi star equals a plus I delta x, right? You start at a, and then you add I times the width of n of I intervals, right? I times the width of each interval. Here it's the left one for the left. And well, there are others too. You can take the largest in each one. You can take the smallest in each one. I'd like to point out the midpoint technique, or the midpoint rule, which is in each subinterval, you pick the height that corresponds to the point in the middle, right? So the midpoint of each subinterval. And this is what it looks like. So from 1 to 1.5, it's 175. Then you evaluate the function there. 125, and then 175 here. 2 to 2.5 is 2.25, and finally 2.75. And your xi star here is going to be a plus I minus a half times delta x. Right? It's essentially the right endpoint rule, but you're adjusting by subtracting half of a subinterval to get you to the endpoint. To the midpoint. Okay, so those are 3 rules that we will be seeing in our class.